Yes, I'm Dave Cunningham. I'm a software engineer at Google. This is basically my 20% project. So it's open source. We launched it about 5 years ago. It's had reasonably good adoption, which is cool. You could call it a configuration language, except when we launched it, that term existed at Google, but it didn't exist really outside of Google, or it wasn't used very much. So the term we used was data templating language, and that's what's on the website. So but these days, you can use either of those, and you would be correct. But what do they actually mean? So this is a configuration language. Can anyone tell me what this is? Nginx, yep, good. What about this one? Make, yep. This one? Puppet. And this one? Yep, that was a lot of people. How about this one? CMake, you guys are good. All right, so we've got 5 tools here, basically 5 different configuration languages. So I would consider this to be a bit of an anti-pattern. Not to dump on these tools, because they're obviously they're really popular, they've done really well. But there's an anti-pattern here, which is that if you're writing a tool, you're writing an application, you need a config file. So what you do is you start off, you just write some simple format, you write some code that can do key value pairs or something like that. And then you start needing more things. You think, oh, I need comments. I can add comments easily, and then I could document inside the config file what all the options do. You could turn off options and that kind of thing. Yeah, cool. Then sooner or later, you get duplication in there, and you want to, say, pull stuff up to the top so you can modify it in one place and just reference it later on. OK, cool. You can see where I'm going with this. There's a lot of slide left. Where are we going to go? So string arithmetic. Maybe you want to compute a URL. You want to put a host name in it or something like that. So you start accumulating these things. Maybe on Windows, you need to do something completely different to every other operating system. It could happen. I've been locked out. I don't know your password. Power. Oh, cool. All right. Awesome. It's kind of like the slide itself, actually. OK. So if you have conditionals, maybe the next thing you want to do is make a few of things that are all quite similar or different in subtle ways. And then how many of them do you want? Maybe you need to compute how many you want, or you want to factor out the number of them to the top or something like that. So you start to get integer arithmetic. And then once you've got all this logic, people are writing combinations of logic. You want to say, oh, let's just take this logic and give it a name so other people can use it. So now you've got functions. And at this point, you're probably already Turing complete, either through the recursive functions or through arithmetic and loops. But you don't stop there, of course not. You want to be able to abstract over data. So you want to say, look, there's this object or thing, and we're deriving other things from it and saying they're slightly different because we're overriding certain fields or adding things or whatever. So you're doing templates or you're doing object orientation or something like that. And then, of course, everyone asks for closures. You've already got functions, but you need closures too. And then you end up with one of those, which is great, except it isn't. So, of course, when you have a language which has been developed in an ad hoc way and you accrued features over time, it's not necessarily the best language if you consider it to be a language from the first instance. So, yeah, you might have complex or surprising behavior. Without a specification, it's hard to develop tools if you want to verify a config or something like that. Because each feature has been added because somebody asked for something because they were trying to do something, features can often end up overlapping. You end up with too many features. The implementation can also be a bit dodgy. And then if you try and improve it, you can't because you don't really know what it was supposed to do in the first place. There's no spec. There's only that one ugly implementation. And the worst case, if you want to move it to a cell phone or run it in the browser and you have to do a complete re-implementation in JavaScript, then you're not in a good place. OK, so what about this option, which many things do? You use a textual templating system, and you expect to generate YAML or whatever, and then you parse it as YAML. So this is using Go templates, actually. And it's not too bad. There are a few things in this that are a bit dodgy, like are we using quotes or not? What if the service type is NO, so it becomes false? But generally, you can at least read it. Alternatively, it might end up a bit like this, which is less good. And we're not going to look at this and try and figure out what it does. OK, so Jsonnet exists to kind of solve this problem, to give you a reusable library or a command line utility that you can use for sort of this configuration problem. And it does something that's very simple. It will just generate JSON. That's all it does. And being basically a programming language, it is an extension of JSON. So basically, in all the gaps in the JSON syntax, you can add other constructs and add ways of computing stuff rather than just putting it in literally. So you can say with a bit of hand waving that it's only got 9 features, 3 of which are from JSON itself. So the first 3, literals, arrays, and objects. There are no arrays over here, but you can see the literals are like strings, and the objects are the bits between the braces. That's JSON terminology, but you can call them dicts if you want. The others, variables, conditions, arithmetic, closures, mixins, and errors, together give you a relatively powerful language. So, and it's multi-paradigm. If you've got variables and closures, you have functions, and those are recursive, so you can do basically functional programming. And the object orientation, you can see it in this example, because when you override self.person, which refers to this here, and change the name, you're also changing what self.name looked up here. So you're changing the welcome message. You can't see my arrow. Oh, well. I'll do it without the arrow. So yeah, what's happening there, that's late binding. So that's object orientation. You have to move it all the way over. That way. There's your arrow. Thank you very much. That's my, I need that. Okay, so the point here is that if you have a small set of sort of orthogonal features, you can create quite a powerful language. It's also quite simple. Also, what this offers you is it's hermetic, which means that it will always evaluate to exactly the same thing, no matter what operating system it's running on, no matter what the day is. You can't have the date in the code and generate different stuff depending on the date. You can't use random number generation. You can't look at the local file system. You can't use environment variables because there might be something in like a bash RC that you put there 3 years ago and have forgotten about it, and then it doesn't work on someone else's machine. So the whole point is that it's going to always evaluate to exactly the same thing no matter what environment it's in, which is what you want for config. And yeah, it's familiar syntax, ideally, and it's concise. So we've got object orientation, but we don't have classes because they tend to clutter it. So it's trying to do the same thing as a templating language where you overlay, you interleave the data with the computation, and everything is nice and concise. And finally, there's a spec with formula. You probably can't see that because of the balloons, but it's okay because it's the least important point. There is a formal spec that describes the behavior of it. And now, hopefully, I can escape from this and just take you to the website. Maybe not. Yeah, what was it? Control. Cool. Yeah. So rather than go through loads of slides sort of showing what the language is, which is a bit boring, on the website, jsonnet.org, these things, which apparently have stopped working. Why? This all worked fine earlier. Let me reload it. All right, I'll just hit enter up there. Cool. Reloading it fixed it. Okay, yeah, so these are supposed to be editable, and you can sort of play around with the language. See, it updated on the right. So that's the one the example that we just had a minute ago. This is a version that uses functions, and this is a more complicated one. You can generate things in languages other than JSON. So this is, if I change my app here, you can it'll update the one on the right. So this is a way that you can sort of play with the language and learn it. And in particular, in here, there's a tutorial which has a lot of those, showing like various features of the language and so on. So if you're curious about this language, you can go to the website and experiment with it. Okay. Cool. Yes, so this is the next slide, right? Yeah, good. So where is this used? It's used a lot in Kubernetes. The reason being that, unlike all the things that I showed you earlier, they have sort of these languages embedded into them. The Kubernetes project decided not to do that. It just has basic YAML. So lots of people wrote tools to generate the config for it, and they used Jsonnet, which was great. And they all of these things are fairly similar in the way that they use Jsonnet, and they differ kind of in what they do afterwards, how they interface with kubectl and provide additional features like secrets or whatever. Also, monitoring configuration. You can generate your sort of dashboards and alerting rules and stuff like that from Jsonnet. Box and Databricks have a whole bunch of their internal infrastructure, and they use it there. I don't think they've open sourced any of that, but they have written blog posts and videos about it that you could look at. And Databricks actually re-implemented the whole language in Scala, which is pretty cool. But they were able to do that because it's a fairly simple language and it has a spec and so on. And Spinnaker uses it in the form of Jsonnet. And of course, these tools here, Terraform, CloudFormation, Deployment Manager, they all will accept JSON, so you can just use it for that. I mean, they accept more sort of richer JSON or higher level stuff, but if you just give them plain JSON, you can do the abstraction stuff in JSonnet instead. So these people are finding that to be good. Finally, anything can really use JSON. It doesn't have to be a DevOps tool. So these Lullaby VR framework and Pyland, these are game engines, and they're using it for things like material definitions where you say, like, I have this texture and I want to put this color on it, or it's shader parameters or whatever. So it's kind of like a similar to config problem. Okay, so there's other stuff going on in this space. At the time when JSonnet was launched, the only one around was Hocon, which was not as powerful as JSonnet. It didn't have the functions of any object orientation, like templating features. It does have variables, I think, and it can substitute stuff, but it's not too powerful. And then later on, Starlark, which used to be called Skylark, which is an offshoot from Bazel. Bazel did exist at the time when JSonnet was launched, but this was spun off from Bazel later. And it's the config language, basically, of Bazel, the one that fulfills the role of like a makefile or whatever. And so this is, it's kind of like, you read it, it's just like Python, and it's very imperative. It has functions, but not object orientation. But that's okay. DAL is from the Haskell community. It uses this system F omega type system, which I'm sure you're all completely familiar with. And the big thing that they claim is great about it is that it's not queuing complete deliberately. You can't write non-terminating programs on the grounds that you don't need to. And that's a property, I believe, of this type system that it uses. So this is a very Haskell-y type thing. But of course, you can still write programs that take an enormous amount of time and memory, even though they do technically terminate. So it's not really clear what the value of that is. And again, because it's functional, there's no object orientation. It's just, you're writing something in basically a functional style, which may not appeal to everybody. A queue is really like trying to think about the problem from first principles. And he's come up with a sort of a constraint language, a sort of logic programming model, which is quite interesting. And instead of using, hopefully that will go away. Instead of using sort of functions and object orientation, it uses disjunction and unification, and it's like writing Prolog to do your config. But because it's so different, it's quite hard to actually compare it. So it's interesting. So anyway, if JSonnet isn't doing it for you, there are some other options. Anyway, so we're here to talk about how JSonnet was implemented and how it was the experience from porting it from C++ to Go. So just to sort of give an overview of its implementation. So like with any programming language, you start off with a string, which is the program, hopefully, or it could be complete junk. And first you lex it, or you get tokens or an error. Then you parse the tokens. You either get a parse error or you get an abstract syntax tree. You then desugar that, which produces usually a bigger AST, but with fewer constructs in it, for the reason that everything to the right of that has to deal with fewer features of the language, and it can be simpler. And then you do some static checking, which will reject the program if, for example, you're using a variable that hasn't been defined, or you are using self outside of an object or something like that. There aren't actually any static types, but you still do static checking. And then that AST goes into the interpreter, and that has a whole runtime engine. It has a stack and a heap and a garbage collector and whatever, and that will churn on that until it produces a concrete value, which is kind of like a JSON tree, you can imagine. And then you manifest it, which is like serializing it and get JSON out. Okay. Simple. Well, it's simple because each of those stages are conceptually simple. Right, so the initial implementation was in C++, and it wasn't too bad. It was quite very easy to get to work on performance, and there was no surprises there. Tried to use standard C++, no POSIX, none of that. So it compiled everywhere, and lots of people wrote bindings for it for various languages, so that was cool. It was kind of challenging to write it, firstly because JSonnet is an automatic memory management language, and you implemented it on top of a language which has manual memory management, so you have to implement your own garbage collector, which is not so hard to do. It's just a depth first search. Technically, it's just marking everything and then cleaning up everything else. But of course, if you have a bug in it, you're either going to leak memory, it's good luck debugging that, or you're going to reuse memory prematurely, which is even worse. So that was a lot of fun. So this next point, so like the most intuitive way to implement something like this in expression language, you can imagine if you're trying to write a calculator that works on doubles, you would do x plus y by first evaluating x, storing the result of that, then executing y, storing the result of that, then adding them together. But in C++, if you imagine extending this to sort of the whole language, you can get stack overflow because you're doing this recursive execute call so much. And you would blow the stack with some quite innocent Jsonnet programs because it's not really clear how big the frames are in C++. And different systems have different stack sizes, and if you're in standard C, you can't control that. So even if you sort of try and put a limit on how recursive you can be in the Jsonnet world, you often end up blowing the stack anyway before you hit that limit. So that was a nightmare. And the other problem is that if you imagine instead of adding numbers together, this is concatenating strings. This one here is going to create a string on the heap, store a pointer to it, keep a pointer to it on the local stack, then go away and execute this, which might trigger a garbage collection, and then the thing where you created here won't be visible to the garbage collector because it only lives on the C++ thread. So it will then free it, and then you'll have a seg fault. So you have to sort of teach the garbage collector about things that are on the stack, and that was also a nightmare. So the solution was instead of using this nice, intuitive, recursive evaluation sort of system, you have an explicit stack. So you have a vector of frames that you can actually look at from the garbage collector, and when you're evaluating, you push things onto it, and then you have a big loop. So basically, it's no longer a recursive function. So that's great, it worked, it was fast, it was fine, except that it was impossible to understand, and although there were lots of users coming in, none of them were actually contributing anything. So in terms of growing the ecosystem, that didn't really work. So you can guess what happened next. So that was the first concern was alienation of potential contributors, and the other one is if you want to run this on the server and you've got untrusted Jsonnet code coming along, you imagine with this garbage collector that you don't entirely trust, it's only a matter of time before someone finds some stack overrun or whatever and owns you. So no one wanted to put it on the server. So both of those are addressed by rewriting it in Go. And Joe Beder, for Kubernetes fame, and works for Heptio now, he initiated it, and then our intern, Stanislav, finished it off. Thank God for interns. I think many projects wouldn't be here today if it wasn't for interns. So the idea is to replace the C++ version because maintaining two of them is a pain. So that's what we tried to do. So the first attempt at this, we had a complete implementation of the language, and it was looking good to start with because first of all, you can use Go as a garbage collector. So no need for any of that. Go's auto-extending stacks means that you've got a lot more headroom, basically, and you can do these recursive calls without it blowing the stack immediately or worrying about who has set what in ulimit or whatever. So that was great. The code was conceptually much simpler, although there were many more lines of it because this is Go. But that's fine. The bigger problem was that it was much slower, 5 to 10 times. So, of course, what do you do when something's too slow? You run the profiler, which showed that the garbage collector was the bottleneck. So that means there were too many allocations. And what's nice about the profiler is it'll tell you where the allocations are coming from. And they were kind of surprising, a lot of them. I guess I at least was fairly new to Go at this point. So things that you make assumptions as you're writing the code about, you have a model of how it's going to perform, and then you get surprised because things are being allocated on the heap that you didn't expect. Some abstraction layers, though sometimes we get sort of layers of nesting that we're using interfaces in two places, and when you made one of those, you get two objects instead of one. So we did stuff, we flattened stuff, we tried to avoid interfaces, we tried to avoid using interfaces. There was one case where it wasn't actually possible to do it, or we chose not to do it, and that is the Jsonnet value. So in Jsonnet, values can be null, true or false, a number, or a few other things that are on the heap, like strings, arrays, functions, objects. So in C++, there was like a 16-byte struct that was copied around by value, and that was a tagged union. And if it was one of the primitives, it would not have a pointer to the heap, and otherwise it would point to something on the heap. Whereas in Go, it's an interface, and like all of those numbers, bools or whatever, are structs implemented in the interface, and that means that it's always on the heap, even if it's something trivial. So we weren't actually able to push down get rid of all of these extra allocations compared to C++. Or I suppose we could have done, but the code was starting to suffer from all of this work to optimize it at this level. So we decided, the whole point of this was to have easier code that could be we could have more contributors and people wouldn't be scared of it. So we didn't want to go down that path. So instead, we compensated by doing much higher level optimizations to get the performance up sort of end to end by taking, so the Jsonnet standard library is, most of it's written in Jsonnet, but of course that's, rather than making the Jsonnet run faster, we just ran less Jsonnet. That's basically the gist of it here. So replacing things with built-ins and doing caching of fields so that we don't run things more often. So as a result of that, Go Jsonnet is actually now faster than C++ Jsonnet, although if we had done these same optimizations on C++ Jsonnet, it would just be faster still than Go. But we want to actually incentivize people to move to Go, so we haven't done that. So there we go. So the honeymoon of being able to use these extensible stacks sort of came to an end. So this is Go code that, sorry, this is Jsonnet code that is doing an iteration, basically, summing the numbers from 1 to n. And this is a tail recursive function, if you know functional programming. And in C++, it would work fine. You'd expect it to take on time, but O1 space, because it's an iteration. And the way that works is using tail recursion optimization. But in Go, because of the recursive evaluate function that we have, it just runs through the stack and actually uses on RAM, which is a waste of RAM first, but also this ends up crashing the VM. So if Go were able to, I mean, technically speaking, this evaluate call is actually tail recursive. If Go did that optimization, this would fix this, but it's probably a bit of an ask for it to do that. So the other option is that we use this custom stack again, and then we don't have a recursive call, but that compromises the readability of it. So because we don't really know what to do about this, we have obviously punted it. But also no one has complained about it yet. And it's because it's really, although it's the same problem as in C++, it's still different because the frames are tiny. You know, in C++ you get lots of stuff inlined and you get big frames. And you can't really control how big the frames are, and it changes depending on what optimization level you have or whatever. But that didn't seem to happen in Go. And also the default stack is a gig, which is not the way it is in C. And even if you want to, you can change the stack size. So no one's complained about this, and it seems that it might be okay just to leave it for the time being. Yep, remaining work. So we want to sort of get rid of C++ eventually, but of course there are people writing C++ code using it as a library. So we use CGo to build a drop-in replacement of the C API around the Go implementation, which is quite cool. And obviously, because it's a self-contained build, this is completely invisible to anyone using it. They could just imagine it was built from C++ still. Obviously, that wouldn't be the case if we used Java or something, so that's quite nice. We've tested this a little bit, but we haven't really started encouraging people to use it yet. The more immediate use for it is to convert the Python module. There's actually a Python API for Jsonnet, which currently uses the C version, and that's the module itself is written in C Python, or whatever it's called, the C API in Python. So we can just use that same C code and use the CGo behind it. And that should allow us to port everyone who's using the Python binding of this over to the Go version. And the idea is that we pre-build Go bindings and push them into PyPy. And then I think on the end user's machine, they will do the last bit of compiling the Python-specific code and bind everything together. JavaScript. So the stuff I showed you on the website earlier, that is obviously JavaScript. It's a JavaScript implementation of Jsonnet, but it's a bit of a cheat because it's just an mscript and transpilation of the C++ code, which I'm amazed even worked, because basically you're implementing a garbage collector inside a language which is already garbage collected. If you think about it, it was a bit insane. But it did work quite well. But obviously, if we want to get rid of the C++ version, we need another way of doing JavaScript. So we looked into Gopher.js. It did generate some JavaScript, and then I didn't get around to running it, and then got distracted by other projects. But that did look promising. And I was just talking to Paul earlier about using WebAssembly instead. That might be better. So we've got avenues to look at there. And finally, there was a formatter in C++ which we're still porting over. That wasn't part of the original tooling, but it's a separate tool, so you can use Go Jsonnet for evaluation and the C++ tool for formatting until that's done. Okay. So, yeah, conclusion. It is a config language. You can use it in tools and applications. It's got a website. There's a separate GitHub for the Go version if you can't find it in the main one. Jsonnet Google group, and the most of the chatter on Slack is actually in the Kubernetes Slack, because that's where all the users are. And this native Go implementation is definitely ready for production use. Plenty of people are using it already. There were performance limitations that we did not overcome, but directly, we were able to compensate in other areas. Basically, it was all fine because we've got a simpler implementation, and that was more important. And we can migrate the C++ version using CGO, which is cool. This resulted in more community engagement. We've got more people contributing, and we've got new tooling coming along. So that is great. That's all I've got.